Hello, everybody. In this edition of the Henstitute, we are going to look at calorimetry. So how do I actually go about measuring this change in temperature? When I add heat something and I change its temperature, how do I deal with those little pieces there? So if you're familiar with this from chemistry, what we do is we have some kind of cup, some kind of insulator that's going to hold your material. And usually what you have is you have some kind of unknown material that might be warm in here, and then you surround it usually by water. Water is probably the most common thing. And the idea is this object is going to radiate heat to the water, and the water is going to change temperature. So we use the thermometer to measure the change in temperature of the water. If we know the mass of the water, we also know what its specific heat is. And the idea is this cup is in here holding this, but we also have an insulator because we don't want this heat to get out, because this heat that's actually flowing out, we don't know what that is. So we don't want this to happen. We want the heat to stay contained in this water. That's the idea of it. So let's try an example. Let's say, let's move myself up there. Let's say that you have a calorimeter. It's made of 0.15 kilograms of aluminum, so 150 grams of aluminum. It's got 200 grams of water, so 0.2 kilograms. Initially, the water and the cup both have the same temperature, this 18 degrees Celsius. And we put this unknown mass in there. So this 40-gram mass is put inside. It's been heated up to 97 degrees Celsius, so it's very warm, and we drop it into the water. We seal everything up. Eventually what's going to happen is everything's going to come to thermal equilibrium. And when this does, the water, the cup, and the material are all at 22 degrees Celsius. So we know the temperatures before, and we know the temperatures after. What we're going to try to figure out is the specific heat capacity of this unknown material. One of the main ideas of this, when I talk about thermal equilibrium, the idea is we're going to say that the heat lost is going to equal the heat gained. When I do that, however, notice that one is technically losing heat, so it's going one direction, and one is gaining heat. So technically, I should indicate one is negative and one is positive, but here in physics, we don't tend to do that. Instead, what we do is when we're finding the change in temperature, we use the absolute value of that change in temperature. In other words, we always take hot minus cold. So we always take the hot temperature minus the cold temperature. If you do that, you should be golden. So here is the example, is what is actually gaining the heat. So heat is being gained here by the aluminum and the water. So I've got the MC delta T for the aluminum. I've got the MC delta T for the water. The one that's losing it, heat lost, is this unknown material. So when I actually am dealing with this, for this change in temperature, we know that the material started out at 97 degrees Celsius and it's going to go down to 22 degrees Celsius. I'm not actually going to put 22 minus 97. Instead, for this delta T, I'll take hot, I'll take 97 minus the 22. So I'm going to leave this as a positive number. Over here, the water started out at 18 degrees Celsius and raised up to 22 degrees Celsius. So for the change in temperature of both of these, we're actually going to be taking the 22 minus the 18. So if you just remember that delta T is always going to be high temperature minus low temperature, you should be set. You don't have to worry about it. So now when I try to solve for the specific heat of this little unknown, what they have done here is they've rearranged it. So we've got everything that's on the left side, the heat gained by the aluminum cup and the water, and then divided by M, the mass of the unknown and the change in temperature of the unknown. What we're going to be doing is we put in the different materials. So the specific heat capacity of aluminum is 900 joules per kilogram degrees Celsius, something we can look up on our chart. It is 0.15 kilograms, and it changes temperature by 4 degrees Celsius. That 22 minus 18, here is our water, it's 0.2 and 4, and we're good. And then on the bottom, the mass of the unknown, and then its change in temperature, which is this 97 minus 22. Notice that I don't have any negatives in there. I'm not looking at loss and gain. I'm always talking about change in temperature this way. When I do that, I get 1,300 joules per kilogram degrees Celsius. If I had a chart, I could probably look that up and potentially know what that unknown is. So this is just an example of how we use a calorimeter and the idea of thermal equilibrium, heat gained equal heat loss, to solve for specific heats, changes in temperatures, masses, whatever we might possibly need. Hope you enjoyed this little edition of the Henstitute.